Hi folks, we're going to take a look at page 146, number 10. So here they're asking us to find the area of the largest rectangle that can be inscribed inside a semicircle with a radius of 10, and they tell us to place the base of the rectangle on the diameter. All right, so again, best thing to do here to set ourselves up is to draw a diagram. So I'll draw a semicircle. Okay. All right, and we're inscribing a rectangle inside this semicircle. And again, the base of the rectangle is going to go on the diameter here. So I'll just draw some random rectangle here. Okay, and I know that the radius is going to be 10 centimeters. All right, and so we want to find the area of the largest rectangle that we can put inside the semicircle. Okay, now right off the bat, there's a couple of ways we can solve this problem. We can solve this problem as a geometry problem. So in other words, just work with the semicircle and the rectangle. But the other thing that I can do, and I'll just draw it underneath, is I can take this scenario and I can also put it on a Cartesian plane and solve it as an analytic geometry problem. Okay, and there's my rectangle. And so here I see that the base of the rectangle can be an x value, and the height of the rectangle can just be the y value on the semicircle. All right, so it can be solved as an analytic geometry problem. I'll solve it as a geometry problem, and in essence, they're exactly the same, just two different approaches. All right, so one thing that we've seen in the past when we've solved these types of problems is to look for a way to connect the two shapes that we're working with. So we have the semicircle, we have the rectangle, and the way we can connect them is, remember that the radius of a circle or semicircle is the distance from the center to any point on the circle. And so in particular, I'm going to choose to draw my radius to the point where the two shapes meet. All right, so now what I'm trying to do is I'm trying to maximize the area. So I know the area of a rectangle is given by the length times the width, but of course our usual issue is these are two different variables, and I need to come up with a function in terms of one variable. Okay, and so here's my length and here's my width. All right, but instead of working with the length, and this is something we've done before, is because I notice, and hopefully you've noticed this nice right angle triangle here, I'm going to work with this value here, x. I'll call that x, okay? And of course we see that that's just half the length. So we have that the length of this rectangle is just going to be 2 times x, all right? And we see that the height of this rectangle, I'll call that y, is connected to x via the Pythagorean theorem because of this right angle triangle. All right, so here what we have is we can write x squared plus y squared equals 10 squared. And so if I solve for y, y is just going to be equal to the positive square root, since it represents a length of 100 minus x squared, and that is just going to be the width of my rectangle. All right, so now notice I didn't quite write y in terms of, I didn't write the height in terms of the length, but I wrote y in terms of this new variable, which represents half the length. So what I've done is I've written the area in terms of this variable x, this third variable. Okay, so the length is just 2x, and then the width is just the square root of 100 minus x squared. Okay, we have exactly what we want. A function that represents the area, the thing we're trying to optimize, with respect to one variable. Okay, the one thing we do want to specify here is what's going to be the domain over which we're working. Well, here we see that x can't be larger than 10. Now, in fact, it can't be equal to 10 because otherwise I don't really have a rectangle. I just have this straight line at the bottom of the semicircle, essentially just the diameter. There's no height. Okay, so it needs to be less than 10, and of course it needs to be greater than 0 because it's a measure of length. So we have 0 less than x less than 10. So here notice it's not a closed interval, so I have to make sure that I justify my optimal value later on. Okay, so there's nothing really here to simplify, so we can go ahead and now do the calculus portion. So let me take the derivative So the 2 is just a constant, so I'll just leave that on the outside. So I need to take the derivative of this function here, and so I'm going to have to use the product rule. Okay, so the derivative of x is just 1 times the second function, so that's just 100 minus x squared. Okay, then plus the first function x times the derivative of the second function, and so here I'm going to have to use the chain rule. So I'm going to think of this as 100 minus x squared to the exponent of 1/2, so the derivative is just going to be 1/2 times 100 minus x squared to the negative 1/2, and then of course by the chain rule I have to now take the derivative of the inside function, which is just going to be negative 2x. All right, and here I see that this 2 in the denominator reduces with that 2 in the numerator. So let's write this out here. So again, I've got this 2 out in front, and let's see what I have. Well, I have square root of 100 minus x squared, and here I have minus, and here I've got x squared is the only thing that's left in the numerator. Okay, and I say that because of course this has a negative exponent, so it's going to go into the denominator. Square root of 100 minus x squared. All right, and of course I'm interested in when this derivative is equal to 0. Okay, so first thing I can do is divide out 2 to both sides, so I don't have to worry about that at all. Just divide 2 by both sides. I just still end up with 0 on the other side. And here, in order to solve this, I'm going to want to write this as a single fraction. Okay, so trick we often use. So here, my common denominators are going to be the square root of 100 minus x squared. So I need to multiply it to this first term because it has a denominator of 1. And of course, root 100 minus x squared times root 100 minus x squared is just 100 minus x squared. Okay, minus, well, this is just going to be x squared since it already has that denominator. All right, so 100 minus x squared, square root. And so now I'm left with something fairly simple to solve. Because it's a fraction, I only need the numerator to be equal to 0. All right, so we have here 0 equals 100 minus 2x squared. Okay, so if we solve for x, I'll bring the negative 2x squared to the other side, equals 100. So x is equal to, so first I have 100 divided by 2, which is 50. And then I have to take the square root of both sides, so plus or minus square root of 50. And of course, I'm not interested in the negative portion here because x is representing measure of length. Okay, so that means there's only one critical point, square root of 50. So I'm going to now test to see if it's a local maximum and justify that it's an absolute, presumably max, since I'm looking for the largest area. All right, so let's do that here. So a prime, so remember I'm starting at 0 and we're going to 10 is the largest possible value. In fact, anything less than 10. And here I got somewhere in between, root 50. Now here root 50 is just over 7 because square root of 49 is 7. So let me take x equals 1 here. So if I go back to the derivative, I'll go back to this simplified version here. Okay, now remember there was this 2 in front, but that's not going to affect the sign. Okay, so if I put in x equals 1, I get 100 minus 1 squared, which is 1, minus another 1, so that's definitely positive. Okay, and then here to the right, let's put, so we said this was around 7, so if we put in 8, let's see what happens here. 8 squared is 64, so 100 minus 64 minus another 64 is definitely negative. Okay, so that means between 0 and root 50, the function is always increasing, reaches our local maximum, and then here from root 50 to 10, it's always decreasing. So I'm talking about the function here, since the derivative is negative. And so this shows that in this interval, this is not just a local maximum, it's in fact an absolute maximum. Okay, so we found the value that gives us the largest area. So now we just have to take this value. I go back to my question and I see that they want the area of the rectangle. They're not actually looking for the dimensions. They're looking for the area. So I can just stick this into the area formula. okay, that I have in terms of x. So I have my answer is going to be given by, so the area is just 2 times, so take a, oh, there it is. Take a look at it, 2 times x, so 2 times root 50 times square root of 100 minus root 50 squared. Okay, and let's see what we have. So 2 root 50. And here we have root 50 squared is just 50. 100 minus 50 is 50. So this is just another square root of 50. So what do we have? Square root of 50 times itself is just 50 times 2 is 100. And since everything was just given in terms of general units, this is going to be units squared. All right, and there's our answer. So let's recap. Step number 1, draw a diagram. Now, whether I work with this as just a geometry problem or an analytic geometry problem on a Cartesian plane, I'll end up with something that works as long as I do it correctly. So I started off by writing my area in terms of a single variable, finding my domain, applied my calculus methods to determine my critical value, and then from there I justified that this related in fact to an absolute maximum on this interval, and then from there I answered the given question. All right, that's it for this one.